In this video, we're going to go over half-life as well as various calculations we can do with half-lives. So to start out, we need to define what a half-life is. Essentially, it's the time it takes for the number of radioactive nuclei present in a sample at any given time to fall to half of its value. It will vary from isotope to isotope, so some can be very long, like Ra226 here, which is 1600 years, whereas the other isotope 224 is only 3.7 days. So like that is a massive difference in terms of the half-life. In the graph here showing here, we got number of nuclei remaining versus time. This particular reaction, if we're starting at 8 in terms of our nuclei remaining, going down to 4, which is half of its value, takes 2 seconds. So the half-life from this reaction is 2 seconds. If we go down from 4 down to 2, then that's another 2 seconds. And then 2 down to 1 is another 2 seconds. So the half-life for this particular graph is 2 seconds long. We can do various different calculations involving half-life. And so one thing we need to know is radioactive decay is a first order process. So that's similar to our rates of reactions where we see first order rates. And the rate of decay then is going to be proportional to the number of undecayed nuclei remaining. The rate of decay is normally expressed in terms of activity, A, which is the number of nuclei which decay per second. So the rate equation looks a little bit different. Instead of writing rate is equal to K times the concentration of our value, which would be a first order process, instead we write A for rate, and then lambda is our decay constant here. And then N is our concentration. So it's actually the number of undecayed nuclei present. And then important to note, A is our activity. Its units are becquerel or BQ, which is 1 decay per second. So seconds is important. If we have other times and we use this equation, we do have to put it into seconds. And that means that our decay constant has units of seconds to the -1. The other equation that's really handy is if we take that rate equation and we integrate it, then we get the following equation. N is equal to N naught e to the negative lambda t. So what do all these things mean? Well, N is the number of undecayed nuclei present at time t. N naught is the number of undecayed nuclei present at time 0. And then lambda is our decay constant, okay? That is the same as, we can calculate it as ln 2 over t of a half, and that's just because we're a first order reaction. So if we do the math there, that's the same as what we would get if we were using the other equation. And then t is our time, and our time, everything's going to need to be put into seconds here because our decay constant is seconds to the -1. So another useful form of this, just to rearrange it, is N over N naught is equal to e to the negative lambda t. And what this gives us is a percentage of the nuclei that have decayed. So it can be handy if we're trying to find masses that are left over after a certain amount of time. And we'll see this in the couple of examples we've got following. Okay, so let's start off with a pretty easy example. We've got germanium-71. It has a half-life of 11 days. If there was originally 2 milligrams of this isotope, we want to find out the mass remaining after 44 days. We don't need to use any fancy equations for this. We can literally just reason it out. So if we have 2 milligrams to start and we undergo one half-life of 11 days, then our definition of half-life is we would have half the amount, so 1 milligram. Now, 44 days with an 11-day half-life means we're going through 4 of these cycles. So let's do the other 3. So if we go another 11 days, half of 1 is 0.5 milligrams. If we go another 11 days, then half of 0.5 is 0.25 milligrams. And then if we go one more half-life of 11 days, we have 0.125 milligrams left. So that's how much would be remaining after 44 days. So really sort of simple, easy way to go through that calculation. Our second example, we've got a half-life of Rutherfordium-104 is 65 seconds. We want to calculate the decay constant and the percentage of a 1 microgram sample remaining after 3 minutes. So let's start out first. First off, we want to find the decay constant. So we can find that because we know the decay constant is equal to ln 2 over the half-life. So we can take ln 2, and our half-life is already in seconds, so that's great. We're just going to leave it in seconds, and that is going to give us 0.011 seconds to the minus 1. So that's our decay constant done. The second part, we want to find the percentage of our 1 microgram sample left. So we're going to use our n over n naught is equal to e to the negative lambda t, and this is going to give us our percentage. So we're going to take e to the negative, and our lambda is 0.011. And then 3 minutes, we're going to multiply that by 60 seconds to get us into seconds. So that's 180 seconds. And we'll pop that in here. And if we do that calculation, we get 0.147. Now, this gives us a percentage in fraction form. So if we multiply this by 100, we would have about 14.7, or I guess really we need 2 significant digits, so about 15% left over after the 3-minute time. Okay, so that's it for this example. Let's move on to example number 3. So in our last example here, we're given the activity of a 1 microgram sample of nitrogen-13 is 5.35 times 10 to the 13 becquerel. We want to calculate the half-life and the mass left after 45 minutes. The mass of a nitrogen atom is this value here. So first off, we do need to figure out the number of nitrogen atoms we have in this 1 microgram sample, just because the becquerel and the activity is based on the number of nuclei present, not on the mass itself. So to find the number of nitrogen atoms we have, we're going to take the mass of our sample, so 1 microgram, but I'm going to put that in grams, so 1 times 10 to the minus 6 grams. And then we're going to divide that by the mass of a nitrogen atom. So 2.16 times 10 to the minus 13 grams, and that's given to us in the question. So doing that, we get 4.63 times 10 to the 16 atoms, okay, or nuclei, or however we want to set that up. So now we can use our activity equation is lambda n, because this now is our n value, not to be confused with nitrogen. It's just a bit of a coincidence there. So from here, we can find our lambda by taking a over n, and we're given the activity in the question. So that's 5.35 times 10 to the 13. We're going to divide that by our number of atoms, and we get, what is our lambda here? We get 1.16 times 10 to the negative 3 seconds to the minus 1. Okay, so we have figured out the half-life. Now we need to know the mass left after 45 minutes. So it can be easiest to start with finding our percentage first. So let's do that. And then we can use our percentage to find our mass. So e to the negative e lambda, so our lambda is 1.16 times 10 to the minus 3. And then our time, 45 minutes. We're multiplying that by 60 in order to get seconds. And so that's going to be 2,700. I can't quite fit it in there. 27. Whoop. Hold on. Wait a sec. Let me just get my tools out of the way. There we go. 2,700 seconds. Oh my goodness. Okay, I'm too close to my toolbar. This is the problem. So when we do this calculation, the percent we get is 0.0442. And we don't need to change that into a percentage, but basically now we're going to find our mass by taking the percent we have remaining, multiplying that by original mass of 1 microgram. So we have 0.0442 micrograms left over after 40 minutes. Okay, so that is our question answered. We've answered everything that is being asked in there. So that's how we can do various different calculations involving half-life. That's it for this video. We'll see you in the next one.